Um, Last time we wrote Maxwell equations in manifestly covariant form, and the other one is just then you go cyclic, right, over these indices. So these are Maxwell equations. And what is the advantage of writing these? Okay, this is by components, and we saw some of the advantages. It's a compact way of writing the entire machinery of the Maxwell equations. And just as an example, if you write the potential, right, the four potentials, so let's take C equal 1, because otherwise I make a constant mistakes. You write the full potential, right? So this is an object that collects the scalar potential, the vector potentials, right? This one we use to derive the electric field, this one the magnetic fields, but and so we can collect them in a single object that has the correct transformations, okay? It's a four vector. When we put these together, it's not that we put apples and bananas. I mean, we take things that transform like the coordinates, right? So this one transforms like the time coordinate, and this one like a space coordinate, okay? You put them together and they transform according to the Lorentz transformations, the way we saw it. In fact, therefore, phi prime, if I do a boost, let's do a boost in the x direction, right? So this is a particular Lorentz transformation in which I boost my speed in the x direction. Therefore, we know that they transform like this. If this is a four vector, so the component there you have the gamma factor. Now there is a c here, but since I took c equal to 1, so it becomes simple. And similarly, the x component of the x component of the vector, space vector part of this four vector transform like the x component of the position, right? And why the other components, because it's a boost in the x direction. Remember that the components that are transverse to the boost are left unchanged. So now you see that some of the results that we derive through computation by solving the Maxwell equations actually are purely kinematical. For instance, if you want to derive the potentials, okay, therefore the electric and magnetic fields for a charge in uniform motion. You remember we did this through rather. We solved the Maxwell equations, and then we specialized that solutions to the case of a constant of the constant motion of your charge, right? But here, this seems to be something that we can solve just by kinematics, because after all, so let's see if I can do this. So I have my original set of axes, my Cartesian axis, and then I boost, so I start moving in the x direction, so in this direction, with constant speed, right? So your charge is here, then you start moving with this, so after time t, it's going to be here. So do you see that this is at rest, and then this starts moving. And so this moves with a certain speed v. Let's put it like this. And you are sitting here, point P, and what is the potential, for potential, but what is the scalar potential and the vector potential that you see from this charge. Okay, but you see, so this is r, that is the distance with respect to the frame at rest, and let's call it r prime, the distance. But you see, then you don't have to do any computation, really, because all you have to do is, okay, I write the potential, so in the frame that is moving with the charge, the potential is very simple, right? Let's call it phi prime, right? So let's decide that the prime, as I did here, is the frame, the Cartesian axis moving with a charge that is moving with a certain velocity v. So in that frame, it's obvious what the solution is, right? What is the solution? If you are sitting here at the point P and you are moving with the frame, then you see a charge that is at rest, right? And the charge at rest has a scalar potential that is what? Yeah, it's just 1 over 4 pi epsilon, or let's forget about this, in these units, it's just, and I have to put the r prime, right? Because it's the distance of the charge from my position in the frame prime, the prime. And what is the vector potential? No, wait, I mean, this is the vector potential of a charge that is at rest. It's zero. There is no vector potential. Right? But now, this is not the problem I was asked to solve, right? This is the problem of a charge at rest with respect to me, and it's just a Coulomb potential, okay? But you see that if I want to know how this, what is the for potential for the same charge that is now moving with respect to me, I just need to do this transformation, right? Because I boost myself to a different frame, right? And now the charge is not at rest any longer because it's moving with speed v. So if I just plug, you see, I can find phi and ax just by putting here phi prime and a prime that I wrote there, and then I derive the potential for the charge moving with constant speed, right? And in fact, you can see there, you just need inverse, right? So you just bring it on the other side. So phi is going to be, so you should bring it on the other, is phi prime, right? Plus VAX. And then you have this gamma factor. Prime. But this is 0, right? So it's just 1 minus v square, this q over r prime. And so you are almost there. The only problem is that you should write this r prime in the unprime coordinates, right? To be, because you are in the unprime frame of reference. So you have to rewrite this. So r prime, right, is the square root of x prime square plus y prime square plus z prime square. Now, y and z, nothing is going on because they are orthogonal to our boost. So the only one that is Lorentz boosted is the x prime. So here you should replace x prime with the x minus vt with the 1 minus v square. Why this? You can simply remove the prime because they are invariant under the boost, because I decide to boost in that direction. So at the end of the day, you have q so you have this square root of 1 minus v square. Then downstairs you have this big factor . And obviously, you can easily derive also the x component of your vector potential, because this we said is simply 0, right? So you see it's just v times, right? Sorry, this is 0. So this is just equal to the v phi. So you just multiply by v. So you should be able to, and the others are just 0. So now you recognize this. These are the result of our computation of the linear vector potential in the case the charge moves with a constant speed. And you see that you have the two effects that are typical of the linear vehicle potential, that you have this sort of squeezing due to this Lorentz contraction in a way. And here you have this retarded time. Remember, the potential is like a Coulomb one, but at the retarded time, because you see this is exactly the retarded time. That, you don't compute the potential from here, but at the retarded time, that is, if this is x, x minus vt, the times. So that's kind of nice, I think, because it gives us, you see, in a purely kinematical way, we can understand these potentials, okay? So this is only for potentials due to charges moving with constant speed, because as soon as they start accelerating, it's a completely different ball game, you understand, because then you have radiation, so it's not a kinematical effect any longer, because you are accelerating, so there is no way that you can boost yourself to a frame in which the charge is it's a rest, because it keeps on changing speed, so there is no such a boost. The problem becomes more complicated. Questions? So how about, so this is the transformation laws for the potentials. How about the field strengths? We saw that this F alpha beta, this is called the field strengths, is a matrix, a 4x4 matrix, the component, antisymmetric matrix, the components, the 6 independent components of which are the 3 + 3 components of the electric and the magnetic field. How do they transform under a Lorentz boost? So you see that they are not 4 vectors, so they are not going to transform exactly like the coordinates as the potentials, as we just wrote for the potentials. It's a little more complicated, but not that much. And it comes from the general, so this is a tensor. So a tensor transforms, always transforms, by definition, transform like this matrix here. So if you have a given transformation of your coordinates that sends you from the unprimed to the prime coordinates, then a vector transform like just a derivative like that, and then you get back the one I wrote. The tensor, so you see it has 2 indices, so it transforms like in a more complicated manner as 2 of these derivatives. So if you now, so this is always true. This is the definition of a tensor, if you want. A tensor, exactly as a vector, is an object that transforms in this way under a transformation of the coordinates. Then you specify what transformation of the coordinates. For us, these are boosts, are Lorentz transformations. So if you do that, you can check, but I just write the results. Again, I just take a boost in the x direction because it's simpler. I don't, so that I have effect. But you see, because of this more complicated, now it is the x direction that is left unchanged. Okay. And the other 2 that gets the boost. So F E prime. So this is the x component of the electric field, the y component. This gets this Lorentz contraction effect plus the, so let me call beta. This is V divided by C. So this is the way the components of the electromagnetic field tensor transform. Those are the electric components. Remember, those are the components of the 0, I, row, and column. And the B, that are the other three independent components, similarly transforms in this way. Okay, so this is the equivalent of what I wrote before for the component of the coordinates or of the for potential. You see, it's slightly different, but what is remarkable about this transformation? Why did I go through the trouble of writing them down? You see, you see B and E gets mixed up. So when you do a boost, the electric field becomes a magnetic field and vice versa, right? You see, under a Lorentz transformation, so for an observer in the prime or unprime frames, what she calls an electric field, you would call it a B field and vice versa. You see, they don't have a independent existence as they did in the original Maxwell things, even though there we already sort of saw these things because we saw that if you were transforming and if you had variation in the electric field, right, a time variation in electric field would generate a B field. But here is deeper than that, right? It's just that if you move with a certain speed given by beta, then you start seeing magnetic fields where before you only had the electric fields. So you see, it's even deeper than the fact that a time varying B or E field generates a E and B field or vice versa. It's just that what you call an electric field and a magnetic field is completely relative to your frame of reference. Okay, so that's what is very interesting about this. And now I can just do the same. So I can compute the electric and magnetic field for a charge moving with constant speed. Of course, I could have done that using the previous blackboard by I compute the potential, so by using the derivative of the potential, I could have, but I think it's more instructive to do it directly by using the E field. And I use the same trick as before, right? So let me, I use the same trick as before, and I draw two frames of references, one moving, so let's do it again. So I have my first one and then the other one that starts moving, okay? So this is X, so let's now do it, so this is X1 in this language, right? So this Y should be X2, so I call this prime, X2, X3, X3 prime, or maybe it should be the other way around anyway. So this is the frame K, and this is the frame K prime, okay? So this moves with the... And let's take now the point here. It's easier this way. So I take my... I'm sitting in P, so that I'm at the origin in the X direction, okay? And the charge, Q, is sitting here and moving with this... and you see, my position with respect to this is identified by, let's call a unit vector that I call n. And I will need this angle here that I call psi. And of course, this distance, when I start counting, is just vt. No? Start from here, then you start moving with constant speed v, or beta, if you use that. And just the same as we did before, but for the fields, okay? So what the position of point P, so let's do Is it for you or? I guess I need this. Well, so the point P. Wait, no, it's answer ask who's there. So the position of the point P, right, in the K prime frame, you see that this position is minus Vt prime, right, when I start measuring. So I don't know, x1 prime, so the position as measured in this frame, the K prime, the frame of reference which is moving, is minus Vt prime, right? Is the amount that you have moved. And x2 prime, so let's give it a name, B, is the distance from here to up there. Now B is B prime, because remember this is the direction transverse to the boost, so this is the moving frame, and this is the frame at rest. And x3 is, well, I pick it that on the axis x2, so this is just 0. So this is the position of the point, the observer point in the, with respect, using the coordinates of the moving frame K prime, okay? So what is the electric field? The electric field here, so let's just compute the electric field here, but as seen by the K prime, so the moving, exactly as before. I ride along this charge, right, very happily with constant speed in that direction, so again, what is the electric field? It's just as before. Is the electric field is the Coulomb field. So so now E1, I guess, in this language, E1 prime, so in the moving frame prime, is just, let's say, minus Q. How should I write this? So is 1 is Q divided by R square, right? So, but let's write it with the components, right? Because so is Q x1 prime divided R prime cube, right? But what is x? You see, x1 prime is just that, right? So let's write it like this: Q over R square. I write it like this. So this is minus Q Vt prime R prime. And remember that R prime is B square, by using Pythagoras theorem, is B prime, but B prime is equal to B and Vt prime square. So this goes down here. Similarly, E2 prime is Q x2, right? X2, so B divided by this R. And E3 prime, it will be Q over R prime cube, but times the third component, so this is 0. And what is B prime? Again, I have B prime 1, B prime 2, B prime 3. These are all equal to 0, right? But we know that because for us this is just a charge at rest. So exactly as before, now I just write this. I just write this in the original frame, in the unprimed frame, by using these transformations. Okay. Um, maybe you may wonder what is T prime with respect to T, right? You see that because I have the two starting out at the same point, I just have the Lorentz gamma factor, okay, in the transformation. So if you want, you can rewrite these now. Well, okay, whatever. You see, now by using this, you can rewrite this using the unprimed coordinates. Let's do just the transformation. So now, if so, I guess this is 1, 2, and 3. So you see that E1, right, is equal to E1 prime. So here I should put 1, 2, and so on. And E1 prime is that thing that I wrote there, that now I can write, so minus QV T prime, I decided to call it, so I want to write everything in the unprime at rest frame. So minus QV gamma T, and then downstairs I rewrite this R, well, but it's a cube, so I write it like this. It's B square plus gamma square V square T square 3.5. And similarly, I go on. I have E2. E2 is just E2. You see, E2 is this. So it's the E2 prime with this gamma factor, and so I write it here. E2 is equal gamma E2 prime, right? E2. So I guess no, because I started with the prime, minus gamma QB, and downstairs B square plus gamma square V square T square 3.5. Why E3 is just 0, right? Because because E3 prime is 0, and then the B is 0, so you end up with just a 0 there. So how does it look? So these are the three components of the electric field. Now the B field is generated. Actually, you generate a three component of the B field that is just gamma, beta, E2 prime. That is just beta E2. Yeah.
On the E2 prime part.
Yeah, I was wondering about the same. If I wrote it in this direction or the other. Yeah, I think I'm using the other one, like this one, because I want to transform back. So then you get this gamma. In fact, then you get the B3, that is this is where this is a plus. Yes, thank you. Okay, so you get also the magnetic field through the same transformation, but let's just stop for a second to look at the shape of this electric field. And of course, you remember, well, that I already, so I use that, so I can. You see, you remember the results, right? The field is like a Coulomb field, but it gets squeezed and shrunk in the direction of motion and stronger perpendicularly. And this you see by projection, right? Because you see that this thing here, this is r square, right? R prime square, right? Was this gamma x square plus y square plus z square, right, in general coordinates. And this you can write as gamma square r square minus gamma square minus 1 y z square, right? This is the relation between r, that is the distance, this distance, in one frame and in the other frame. So all I want to say is that, so this is gamma r square, then you can collect this, you see, and you get minus, and what is this? This is the angle, you see, is the sine of this angle, right, when you collect that. So you have this beta square, the sine of psi square. You see, this is the this is the projection along those axes of r, right? Well, actually, against the other direction. So you get the sine of that angle. So in other words, downstairs here you can do the same, and this becomes well, this is minus there. So this was r prime. So I replace with that, I get minus q v gamma t divided by, so gamma cube r cube 1, so beta square, that is v square divided by c square, but forget it, 3.5. And the same up here, gamma QP divided by the same factor. Well, I like beta more. So you have two components, so you pull them together, you get the vector relation. So the vector E is QR, pointing in the R direction, R cube, gamma, you see you have a gamma here, gamma here, gamma here, gamma there, so you have a gamma square. Then this VTB, they reconstruct the R vector, you see, because these are the components. R is this, so this is the x2 component, and this is the x1 component, so I can write this as the position R. And you get, so you get this contraction, gamma square, but on top you get this sine square of psi. So you see that what happened, you have a dependence. This field is not symmetric as it is in the frame in which the charges are rest, but it gets a dependence on this psi. And how is this dependence? Well, if this angle is such that sine of psi is equal to 0, right, you see that this field goes like, so the E field, the intensity of the E field goes like QR square, because these are, no? Gamma square, okay? If in the opposite limit, when the sine of your angle is 1, right, you see, then actually, you see, if this is 1, this simplify, you see, it's like a gamma 3.5 upstairs. So then the E field goes like Q gamma divided by this R square. So these are the two possibilities, the two directions. Then you see that when you boost, you keep on boosting now. So beta goes to 1, and gamma goes to to infinity. So gamma goes to infinity, then this goes to 0. Gamma goes to infinity, this goes to infinity. So what happens is what we draw, well, I don't remember if I did it, but the electric field, right, starts out as a symmetry. If these are the, if you are at rest, right, these are the force lines of this field. But you see that, and the density of these lines is proportional to the intensity of your electric field by convention. Then you start moving in direction v. Then you see that in the direction of the motion, right, you see that the field becomes weaker and weaker, right? So here it gets depleted. On the contrary, in the other direction, this direction perpendicular to the motion, it becomes stronger and stronger. In fact, it diverges as you get closer to the speed of light. So this field becomes something like this. All concentrate. This is the V. This is your charge. And the field becomes, and no field here, all the fields in this cone. And ideally, if you take the limit, it becomes a shock wave. Right? No, like on the ocean, the shock wave. And so this is, we already saw that in the original very long computation that probably you have forgot by now, but now we rederive that again just by kinematics. It's because you are boosting that a field that look like this becomes like that. So if you, if you come running very fast toward a stationary charge, you won't see the Coulomb field. You will see this like shock-like field. It is like a wall. So a photon coming to there, that's what the photon, well, it's too small to have eyes, but would see. Okay? So that was to convince you that this four-dimensional space-time way of writing the Maxwell equation is somewhat useful, besides being very elegant. And now well, is there any questions about this? I hope by now you are familiar with this field. Well, so just retain this as a message. The way you see the field. This is the linear Wecker potential or electric field in the case the charge is moving with constant speed. This is the best way to derive it. Yes?
Are these results are applicable in some frame which are rotating?
Rotating.
Yes.
But rotating is not inertial, right?
Yeah.
So there you have an acceleration. If you start rotating, you start seeing radiation, right? So this is only, as I said at the beginning, this is the kinematics of, so it's a purely kinematical effect. It's just because I'm looking at the same system in two different frames of reference. That's why I call it a kinematic effect. There is no dynamics. There are no forces here. So if you start accelerating, it's a different story. Because in general, if you accelerate, I mean, it's like in mechanics, right? If you start going around, then you start worrying about this Coriolis and centrifugal forces. I mean, you cannot mimic that through a transformation.
So we can only apply this formula
for a charge that is moved. No, this is Lorentz, but I'm thinking this is the Lorentz transformation. The message here is, I guess, that you can rederive these fields just by changing through a Lorentz transformation. So there is no dynamics there in those computations that we did. We solved the Maxwell equations, but it was just the effect that we were looking at the system from a different frame of reference.
Yes, but what is the characteristic of the frame
that it moves with constant speed.
So,
So it has zero acceleration.
yes, that is,
That's-
that has some Galilean.
Yes, yes, that's the definition of inertial frame of reference. In fact, what is hard is to understand the Galilean stuff. Once you have understood that, the only information you need is that instead of doing a Galilean transformation, you do a Lorentz transformation. That's the only new ingredient that Einstein is asking you to apply. But for me, I think for the students, what is difficult is to understand the inertial stuff, the fact that the physics is the same for all frames moving with constant speed. Once you believe, you buy that, then you are done. Because then is a detail if whether x prime goes to x minus vt and t prime goes to t, or you also have some stuff here and then it's the Lorentz boost. Forget about the gammas and all that stuff. Is that clear? So once you understand that observers moving with constant speed with respect to one another, they see the same physics, and they only have to transform their coordinates, as I did here on the blackboard, from one frame to the other, then it's just a technical detail that you should transform using the Lorentz transformations rather than the Galilean one. But conceptually, the idea is that. Is that answering 10% of your questions?
What factor are going to change if the observer was moving too?
Oh, that's, I don't care. I mean, as long as our relative velocity is constant, I don't know if you. The point is that I don't know whether you are at rest or you're moving. That's the main point of the invariance. I have no idea if you are you moving or at rest. I don't know. I cannot tell by using this physics. I mean, all those examples in the books about the guy on the train moving on the ship, right? They are exactly this. If I close you in a train, and you don't know whether the train is moving or not, because if you drop this, it will drop also in the train, right? It's not that we did that exercise even for the Earth. In fact, the effect is very. It goes in the opposite direction. Yeah? But there, because it's not an inertial frame, but if it's an inertial frame, there is no experiment inside a closed room to decide whether you are at rest or moving. In fact, it doesn't make sense. It's one of those questions that you are not allowed to ask. If you start accelerating, then it's a different thing, because acceleration, in a way, you know, if the room starts accelerating, you know immediately, because you start bumping. It's like the bus number what coming here, right? But there, it becomes a different. But there, the generalization of that idea is that you don't know whether you are accelerating or you are in a gravitational field. You see, that's the next Einstein next step. Okay. Good. So now I want to, in fact, go back to our knowledge about mechanics and write down the Lagrangian that gives us these equations, right? Because that is the final point that I want to teach you. Because after all, I mean, we learn all the stuff about Lagrangian, so it cannot apply only to springs and particles. And you see, we have a little bit of a problems here, but in fact, I'm not sure I will be able to, because we have two problems. First is that the Lagrangians that we wrote up to now, they were not covariants, or in fact, they were not written in this language. In fact, we have to learn how to write a Lagrangian that is invariant, right, under Lorentz transformation. So that's the first problem. And the second problem is that we never apply this Lagrangian stuff to a system that had an infinite number of degrees of freedom. Because you understand that an electromagnetic field has an infinite number of degrees of freedom. So it's not the garden variety of physical system that, you know, I always put this QI for our generalized coordinates, but clearly here we don't have even if I had an infinite number of these, here it's worse because it's a field, so it's a continuum. So it's not a numerable infinity; it's a higher order infinity, right? Because it's you know, the difference between the number, I don't know, of natural numbers. Those are infinite, clearly, but they are much less than the of real numbers. You learned that, right? Did you? You know that, right? I mean, I cannot. I mean, they are taping, so I cannot. I mean, this is a higher order infinity than this one, right? And here is the same problem. We discuss a number of degrees of freedom, never an infinite number, but in principle we could. But we always thought that we could map them into the set of the natural numbers. But a field cannot be mapped. It's a continuous function. It's the power of the continuum. So okay. So we have to generalize also that, but probably that is not going to be very hard because we sort of know that as long as there are no mathematicians in the room, we can replace the sum with an integral, and that will do the trick. So let's try to begin this. So my first problem is, what is the action? You remember the action is the right. The action is the integral of the Lagrangian over time. But already here you see a problem, because what is time here? Now time is just a component of a 4-vector, so we cannot use that because the action must be a scalar, but it should be a 4-dimensional scalar, not a 3-dimensional scalar. It should be invariant. So by invariant, the Lorentz boost. So one thing that we know that is an invariant on the Lorentz boost is the distance, the 4-dimensional distance that I call delta S. So I guess it must be proportional. I put a minus for some reason, but to an integral over a distance ds in the 4 dimension. Okay, and by definition the action is the integral from T1 and T2 of the Lagrangian. Okay. So you see that by looking, you see what is ds is c d tau, right? Is c times the proper time of the particle. So here just a single particle. So if I measure the distance on the path of this particle, right, then I have something that is the proper time, that is parameterizing the motion of the particle, and therefore, okay.
I think minus is square, minus is square before.
What?
I think, is there a minus now?
Ah, here. No, but let's see. This minus sign, I don't even remember where I put it.
I think this one is minus c d tau. ds.
This?
No, yeah.
It depends on the signature. So I guess I use the other signature here. So let me keep this signature for a second. So all I want to say is the d tau, right, is what is the relation between d tau and dt? You remember, it's just a gamma factor, right? So so it's dt 1 minus this v square over c square. So then if you replace in here and then you compare, you see that the Lagrangian should be this minus alpha c 1 minus v square over c square. So that seems to be the Lagrangian for a free particle. By using this argument that my action should be an invariant, so it must be some integral over the proper time, then I connect the proper time to the what we call time, and then I use the usual definition of the Lagrangian to be that object that integrated over the ordinary time gives me the action. what is alpha? Well, this, of course this is an argument about invariance, so we cannot fix the absolute value of this quantity. But that comes from looking at what is P, right? Because I know that P, whatever I'm doing, must be the derivative of the Lagrangian with respect to the x dot, right? The q dot that I can call the v, the velocity. So, no, right, this is a v. So I take the derivative of my Lagrangian and I get alpha v. So that's why there was this minus, I guess. Alpha v, right? And then you get this downstairs. And then if I look at the well, now already sort of know what alpha is, but just to convince myself, let's write the energy now. So the energy is, you remember, the energy is the Hamiltonian. This is a single particle, 1 degree of freedom, so is P dot P times the Q dot, so P dot V. So you see P is this dot V, so I get
if I differentiate this,
look, pull out a C.
okay.
So then you have C squared minus V squared. No?
Okay. Okay. I pull out, it's minus alpha c squared minus v squared. If I differentiate this, e squared what minus 2v c squared minus v squared. If I want it to this form, I get
So you say there's still a C.
1 over c, 1 minus v squared, c squared.
So let me just see, because here I get alpha C squared alpha C squared plus alpha V squared. Anyway, you see that from here that alpha must be the mass, the rest mass of the particle, okay? And
You can define another parameter alpha, which will contain.
okay, well, no, but because I know that the Lagrangian is minus MC. So I guess maybe this is not correct, right? So that would be what? Alpha. I get a C here. Maybe this is okay because then I get. So I don't get the C. Okay, I'll check it and I'll let you know. Anyway, you see that this is still not what we wanted, even if I had got the C right. And you see, you see that I can write this. So what I want to say is that if you write it in here, you see the Lagrangian is just this, right? This is the Lagrangian, but if I insist on writing the Lagrangian by using the proper time, right, not measure using t, then I get this Lagrangian. Then I have the four dimensional Lagrangian, so to speak, that is just going to be mc divided by gamma, then the square root of, I don't know, the for velocity I call it u, I think, right? And if you take minus, if you take the invariant frame, you see, this is the way you write that Lagrangian in an invariant form, right? Do you well, it doesn't matter, but it doesn't matter. No, but they are the same. It's just I rewrote. You see that the gamma is this factor here, right? 1 over gamma is this factor here. Then here we said it's the mass, so this is the mc. Then it's just a matter of right. This is just c squared. So this is just mc squared divided by gamma. That is exactly what you have there. So they are the same, but I rewrote them by introducing the 4 vectors, because now I can take the derivative with respect to that and the coordinates and produce the Lagrangian equations. Okay, in a 4-dimensional invariant formalism. But you are correct. So these two are equivalent. But it's correct that the Lagrangian is not unique, as you know. And in fact, you can write other forms of the Lagrangians, but for instance, without the square root, it's still okay. You still derive the same Maxwell equation. But this, you see, allows you to write the, so minus mc, so the action. Then you write everything using the proper time. So this is the Lagrangian written in this form, right? And you see the nice thing about this is that I can write this factor now. This factor here, I can write it as minus mc using the coordinates, right? Because this is dx alpha d tau, so dx alpha d tau, right? So you see that I can just have here the d tau simplify, and I get the square root of the dx. So this is minus mc. I can pull out this and do with the like say this is the scalar product, so I write the matrix maybe eta alpha beta dx alpha dx beta, right? So this is nice because you see this is just the ds, is the distance in this space. Remember, this is the Minkowski metric, right? But actually, this is good for any matrix. You could replace here a generic metric, and this would be the action for a free particle on that metric. This is, in a way, is the idea of general relativity, right? That you study the motion of a particle in a generic metric. But let's stick to the Minkowski metric, and you see that when you write if you do the Lagrangian equations of here, you get immediately the result that the second derivative of your coordinate with respect to the proper time, they must vanish. But this is Newton equation, right? The acceleration is equal to 0 for a free particle, obviously. So this was just to translate into this language the Lagrangian, but really I want to write now the Lagrangian for a charged particle. So this was a point particle, free point particle. How does it couple to the electromagnetic field? It's a term that I have to add to the Lagrangian, either in this form or in the other form. And then you have to remember that you see the acceleration, that what we wrote the other time, that the acceleration of a charged particle right, the Lorentz force can be written in this form here, right, F alpha beta u beta. Right, this I showed you last week that this is equivalent to the Lorentz force, so dt equal E plus the u cross b c in this unit, and dE dt equal EU dot v. Right? Lorentz force in this language is not only the Lorentz force, is also the energy, the power produced by this interaction. So these two are written in this form. And where this, okay. So you see that if you want to produce these equations, you have to introduce a further term into the Lagrangian. I see now, let's see. So I think that, yeah, there is a c square, because now I see that the next page I wrote the Lagrangian like this. So does that work now? Okay, so good. And you want to add this interaction, so now without spending more time, I just write this result. If you add a term like this, u alpha a alpha, so this is the interaction, okay? You see the 4 velocity times the 4 potential that when you do the Lagrangian equation is going to give you this Lorentz force. And what is this in three-dimensional language? You see that, remember that the component, this was phi and the vector potential, so you get minus E phi plus E over C u dot A. So this is 4D, and this is in 3D. So if you want to stick to the 3D, that you use this u vector, then this is the Lagrangian. So this is for the free particle, and this is for the particle interacting with the scalar and vector potential. This can be grouped together by this invariant term, but then here you write it as I wrote it before, as the square root of minus. It doesn't matter. So either, so maybe I should write it. So this, you could write it also minus mc gamma square root of minus u alpha, right? So if you do the Lagrangian equation, that I don't want to do, but you get, as before, the acceleration using the proper time, you get it here, but instead of being equal to 0, is equal to EC. Then you see you take derivative of that alpha, so you get d alpha d beta minus d beta a alpha times the velocity. And if you remember the definition, this is f alpha beta. So you see, you get exactly the Lorentz. So this is the Lorentz force in 4D. So I guess force is not proper. In 4D is not. There is an interesting, so that would so now you know how to write the Lagrangian for a charged particle, and by taking the Lagrangian equations, you get back Lorentz force. Okay, and there is an interesting observation to be made here, that if you write the momentum conjugated here, right? So this is dl dx alpha d tau or ds. If you do that, okay, you see you see that you get the usual term, the mu alpha. This is what is the usual 4 momentum, right, that comes from the 4 velocity. You just multiply by the mass. But you see, you have so this is the u alpha, right? So you have a u alpha also here. So you get an extra term. So the momentum is not just the mass multiplied by the velocity of the particle. You get an extra E over C A alpha. So you see, this is a situation in which the conjugate momentum is more complicated. Okay. And therefore, so you see the vector, the 4 potential, but also the vector potential, if you decompose this in 3 dimensions, is like a component of the momentum. So a particle in an electromagnetic field, a charged particle, gets a momentum that has a component that is proportional, a component of your momentum is proportional to the vector potential. And now you can write the Hamiltonian, because you know the 4 momentum, so you can go from the Lagrangian formalism to the Hamiltonian formalism, if you still remember the thing. And you see that the Hamiltonian is just the p square over 2m, but the only thing you have to be careful is that the p is now this. So in other words, the Hamiltonian is 1 over 2m p alpha minus this a over c alpha times p alpha minus a c alpha. So this is the p square. And you have to subtract the rest energy of the particle, usually, for the Hamiltonian, but it doesn't matter. I mean, this way, you have a nice limit of the energy into the non-relativistic limit. Otherwise, you get always this extra mc square that is there, but... because I think that's what gives you 0, but after the embarrassing of the C, I'm not sure. And then you can write, I wrote the Lagrangian equation, so now I write the Hamilton equations. Well, one, as usual, the first one is just the definition of P alpha, right? And the other one is the one equivalent to Newton's law, and if I'm correct, it should be this. In fact, I have an index that is wrong. So this should be, I don't know, gamma. So this is the F alpha gamma, like this, right? Okay. There are 2 strange things about the you see, the first is that the Hamiltonian, it's a Lorentz scalar, right? In this, that's a bit odd because E, the energy, is not a scalar, right? In this language, is the time component of something. So here you lose this connection between the energy and Hamiltonian that is so nice and natural in the usual thing. Moreover, on the mass shell, as he said, on the equation of motion, the Hamiltonian so defined always vanishes. Relativistic Hamiltonians are always equal to 0 if you put the solution. So that's too, it's a bit odd, and frankly, I'm not, I don't want to comment on that. Questions? So at least we fix this C, right? And so now I have left to very quickly, because it's a little bit beyond, to write the Lagrangian for the electromagnetic field. You see here I wrote the Lagrangian that gives rise to Lorentz force, but this is only, yes,
No, just I want to ask a question because since the beginning of this course, I never listened about Einstein. I don't know. Maybe.
about
Einstein.
ah?
Albert Einstein.
Einstein. Ah,
You did,
well, I mentioned. What do you want to hear about
no,
it?
I want just to listen about him because since just Lorentz.
Ah, you feel that I'm unfair with... no, I said that...
Maybe just a little bit.
but what? I mean, I don't know what to...
This relativity, I think Einstein is the father of relativity.
Yeah, but here is a very practical approach. You see, my idea was that I was teaching you the electromagnetic field.
Yes.
And then you look at the transformation laws of the electromagnetic field and you discover that they are invariant under Lorentz. They are covariant under Lorentz transformation. That's all you need of relativity here. But everything is in there because you have that velocity. You see, relativity what is just the fact that you have invariance under this, that all observers moving with the same, with constant speed with respect to each other have the same laws, right? And then you connect them by Lorentz transformation. So I've told you everything. What else is there? What are you thinking? I mean, there is no more of that. I mean, it's very important, but from the point of view of the machinery, it's just now here is included in the machinery. The machinery already works for you. You don't have to think every time, what did Einstein say? You just use the 4 vectors, and then you are sure that everything you write is covariant under the transformations. No, but otherwise, what you have in mind? I'm not sure. What you want to? I mean, the rest is just the story, how he got the idea. No, but I mean that's.
Maybe not the story, because you have just the name of Lorentz. Because I know the father.
But relativity is the invariance of your system under Lorentz transformation. Period.
Okay.
The rest is just. Advertisement. I mean, I don't know. Just you must be sure that your system is as before in mechanics. We had to be sure that the system was invariant under transformation from frames moving with constant speed. Right. This was guaranteed by the fact that the force was equal to the acceleration, not the velocity. Here's the same. I mean, once you have put this into your formalism, then you don't have to worry. I mean, that's good because you don't have constantly to worry what is correct or not. It's built in the formalism. If you write the Lagrangian in this form, I mean, the physics is automatically invariant under these transformations. Well, invariant. They covariantly transform under they remain in form under this transformation. As I said, you don't have to worry about, we discussed a little bit about this twin stuff, but really, in the everyday life, you don't have to worry about those. Everything is fine, and you stick to this formalism, and you never be wrong. Is that satisfactory? I mean, the rest is, is the history of physics. You can have a class on that. How Einstein came up with this idea, or